Okay, so thank you very much to the organizers for giving me the obsession of looking back at the history of the tau-neutrino and also the determination of the number of neutrinos. The third family of neutrino, the history of the third family of neutrino begins the discovery of the new lepton. You have seen the pictures which demonstrated the existence of the tau lepton, namely typically an electron and a muon and missing momentum. The spectrum of the electrons or muons match very well those from a weak decay via V-A interaction. At the time of 1975, the new lepton was called U as unknown. A couple papers, that's the first paper here. There was no mention of the name of this particle. It took a while to convince everybody. The presence of neutrinos was used as a proof that the new particle was a lepton. This is obtained from a paper by Gary Feldman where he retraces the history of from 75 to 77 until the tau itself was accepted by the community. But typically, this missing momentum and energy was scrutinized. Are the two missing particles in each decay, are they photons, neutral kaons, or charged particles? And here is the description of the fact that only at most 40% of the total number of tau events could contain something else than neutrinos. So the missing particles had to be neutrinos because that was the only thing left. So that's a demonstration that the neutrino was very central to the discovery of the taus. The name tau itself appeared in 1977 and was very carefully chosen. Properties of the proposed tau charged lepton, the same group from SLAC LBL corroboration. And the reasoning that you find in Gary's paper, it had to be Greek like mu, and tau was chosen for triton, which means third. So the tau was carefully chosen. The new tau name just appeared. There was no description of how one chose to call the neutral particle tau nu, but it sounds like the most natural thing to do. Now, measurements of cross-sections and decays by several experiments, both at Spear, even Pep, Delco, also Pluto and the ASP at Doris, quickly showed that the tau lepton was a spin 1/2 particle and tau per cross-section was equal to that of a muon pair. Asymptotically, the ratio would go to 1. The tau decay into leptons and two neutrinos, and the decay is V-A. This is an example of such a spectrum from the Delco collaboration. And maybe more strikingly, the tau decays into hadron and one neutrino, for instance, the two-body tau to pi nu. It also decays into rho, K star, A1, etc., all consistent with a weak axial vector current. All this implies the existence in tau decays of a spin 1/2 weakly interacting neutral particle with the mass below the measurement limit. This flat spectrum from the pions in tau to pi nu is a real demonstration of that. That is what we call a neutrino. If I had a Trivial Pursuit game and I said, what is a spin 1/2 weakly interacting neutral particle with mass below measurement limit? The answer would be neutrino. That's a paper from the pion neutrino, which I found most spectacular. I discovered it last year when they asked me to do this report, and I discovered I had signed it. That was a bit embarrassing. I remember having been asked to give comments and never bothered, of course. But this was a very clear signal of the existence of a neutrino. The question was not whether there was a neutrino produced in tau decays, but whether that neutrino was a new one. The situation is in fact very similar to the discovery of the second neutrino. There was absolutely no question that there was a neutrino in pion decay. The question is whether that was the same as the new E or a new one. That's the question that Steinberger wanted to answer, and Lederman and Schwartz and company. So if you replace this by pion, this is the question that was answered by the 1962 experiment. So how would one answer that question for the tau? I'm sorry, my slide's a bit bigger than the screen. Just to put things in perspective, at the time of the tau discovery, 1977 was when the upsilon was discovered. The B quark had been discovered, decaying into charm. B quark does not decay into top because the top is too heavy. So one could imagine a similar situation for the tau, where for some reason the decay partner, the isospin partner of the tau, which by definition we would call nu tau, would be too heavy or would not be produced. And this hypothesis will imply that what we see for neutrinos would be a mixture or a combination of nu E and nu mu. This hypothesis would imply that the tau lifetime would be very long in the same way that the B lifetime was much longer than what you expect from a weak decay. It was actually a factor of 10 longer. And that would be one thing. And the other consequence of that hypothesis is that the tau could be produced in neutrino beams because you would have a coupling to nu E and nu mu. To demonstrate that the tau was a new particle and the weak isospin partner of the tau, one should demonstrate that the coupling of the tau to its neutrino has a full weak interaction strength. That you can do if you measure the tau lifetime, or you can do if you see W's to tau nu tau decays with the same rate as W to E nu E and W to mu nu mu. Now, the tau lifetime seems very trivial to do for us with vertex detectors and silicon trackers and so on. At the time, there was no such thing. Mach 1 had magnetostrictive chambers, Delco similarly. So those detectors were not able to really measure the tau lifetime. The second thing you need to do in addition to this, so check that neither nu E or nu mu couples to the tau. So these arguments were put together by Gary Feldman in 1981, and he looked, because he was working at the time, I think in Mach 2, that the first measurements of tau lepton lifetime combined with the absence of tau production in a CERN neutrino beam dump experiment excluded that scenario. So this is Gary. He's actually here in the room. I just saw him. Hello, Gary. So I feel a bit embarrassed to talk about his paper in front of him, but the other previous speakers had an easier time that way. So the explanation is just what I said. You look at, you assume that what they call nu tau was a mixture of nu E and nu mu, so a quantum state made of superposition of the two. And then you look at what is the result of the tau lifetime measurement, and what is the result of the fact that the bubble chambers did not see an anomaly in the appearance of nu E's and nu mu's in the beam dump. And you find that the tau lifetime measurement, which was a bit shorter but consistent with the expectation, you would expect this number had to be smaller. I can't really get it. So okay. So from the absence of electrons and final states of nu interactions, one would expect this coupling to the electron muon to be very small. From the excess of neutral currents in the beam dump experiment, one expected this result. And so the combination of the two was that this this fraction of nu-mu's and nu-e's together would be less than 37.5%. Now, the tau lifetime implied that if this the nu tau was composed of these particles, therefore the lifetime was entirely due to nu-mu's and nu-e's, you would get this number, and the combination of the two is inconsistent. Now, arguably, the statistical significance of excluding those things at the limit of the 90% confidence level wasn't so great. But the argument was there. So, okay. So that was in 1981. 1982, closing date January 1st, so the PDG listed the tau-neutrino as an established particle with spin 1/2 and a mass less than 250 MeV. Okay? So if you believe the PDG, like every one of us does, this was an established particle. Now you note that the lifetime measurement is still very poor. There's you also note that there's already a large number of decays, hadronic decays mentioned. In particular, the K star to rho ratio is consistent with Cabibbo angle, which is really a trademark of the weak decay. What is not listed is that the decay proceeds at V minus A, and in fact, the PDG never really went into listing the chiral couplings of the tau-Zorich neutrino. Okay, now the full listing says as follows: existence indirectly established from tau decay data combined with neutrino reaction data. It doesn't give any more details. See, for instance, Feldman 81, Kirkby, etc. Now, what I'm annoyed by this, it was fine in 1982. Indirectly is something I'm a little bit annoyed with, because the detection of the neutral particle from tau to pi nu is perfectly direct. I mean, I will mention another example where this is not something that one could call indirect or model dependent. This note, this is the second thing I'm a bit annoyed, is this note was left unchanged since until PDG 2002. So for 20 years, that's the whole information you had about whether the tau-neutrino was established or not. In 96, the lifetime was already known to 13%. There are several measurements of the lifetime. But more importantly, came a very improved experiment on neutrino search for nu-mu or nu-e oscillations to nu tau and limit of the coupling. That's from the Fermilab E531 experiment, was published in 86. And basically, this experiment strongly improved the limit on the search for tau-neutrino appearance in the beam of muon neutrinos and 3% nu-e's. They didn't see an event out of about 2,000 events, and showed that most tau decays may contain a neutral lepton other than nu-mu or nu-a. Now, the equations here are different than those of Gary Feldman, but it's exactly the same idea. The lifetimes are expressed in MEVs, and so you compare the 4 10 minus 10 MEVs here that the prediction gives, and what it would be if the nu-e or nu-mu were the tau-neutrino, and they are much smaller. So this is really like 8 standard deviations, and for modern standards, this is an absolute demonstration. So I think this establishes the neutral particle observed in tau decay as the nu tau, the weak isospin partner of the tau lepton, which was listed as established particle as of PDG 1982. So by 1986, the tau-neutrino was solidly known and established. Now, it was known and established for whoever would care to read those papers. There was very little publicity for all this. The reason I got to read it is because we measured the number of neutrinos 3 years later. So you needed to put all this information together and write a few equations. several, mostly neutrino physicists, continue to request that one should directly observe the tau-neutrino interaction with matter to be convinced. Now, what they didn't realize is that since you had observed tau 2 pi nu, it implies if one make a beam of those guys, you would necessarily see tau-neutrino, taus appear. Also, the tau, that state is a combination of nu mu and nu e. So really, there was, I think, a more emotional reaction. Now, another problem I have with the direct and indirect wording. I think I've been hit by this direct versus indirect question several times. I think it relates to how many equations good understanding requires. If you can deal with 0 or 1 equations, it's called direct. If you need more than one, it's indirect. So I think we can do better than that. And a scientific organization like PDG should probably refrain from using these words. One should use model-dependent, model-independent. That's meaningful. But direct and indirect is very subjective. I read this. Does the tau neutrino exist as a particle? Surprisingly, that was in 1991. This question cannot be answered by yes or no. Its existence can be proved by direct observation of the charge current reaction. There's no reference to a particular model in which that would be true, and so it's purely words, okay? It's not based on a particular scientific process. Now, you find this in many places. I'm sorry to say, but De Negri, Sadula, and Spiro, in that beautiful article, indulge in this direct and indirect business. In 1985, the observation of the WDK W to tau nu was reported. That's a landmark, too. It was also the first time that the tau neutrino was observed that was not produced in tau decay. So W decays tau and a tau neutrino. So you can see the tau decays into 3 prongs. That makes it easier in UA1, and the reconstruction of the transverse momentum of the tau neutrino. So by 1987, the CC coupling of the tau was established to be equal to that of the electron. And of course, the CC coupling of the tau neutrino was established to be equal to that of the electron neutrino, to plus minus 20%. That's what you find in the PDG at that time. The WDK is precisely what we use to define the neutrino flavors. I was at that school giving a lecture on God knows what, and Boris, who is my reference in neutrino theory, explained that the neutrino flavors are defined by the specific flavor by WDK. Okay? This is an electron neutrino, mu neutrino, tau neutrino. Now, the reason we do this today is because there's a lot of physics we know also from neutrino oscillations. This is a kinematic reconstruction of tau neutrinos that was made possible in E plus T minus 2 WW to hadrons and tau nu tau. You actually reconstruct both neutrinos in the W decay and that from the tau decay. You can count the kinematics as 7 constraints, and we can get the momentum, the 4 momenta of both the W's and the taus. So LEP saw several thousands of those events. LEP also measured the tau lifetime. This is the Aleph number in 1998. Nowadays, there are better numbers also from the B factories. Geta to G mu was, so that's the coupling of the tau neutrino to the tau, and that's the coupling of the muon neutrino to the muon. And that's good to about 4-5 per mil. And the same for the ratio with the electron. In 2000, a beautiful observation was made of neutrino interactions producing taus. That is really a very spectacular signature and absolutely lovely. There's a little bit of small print. the beam was very cleverly made to contain 5% of tau neutrinos from ds to tau nu decays and the subsequent decay of the tau to a new tau. So this is the main source of this. Of course, there are uncertainties in the ds production and in the branching ratio of the ds, and estimated at 20% uncertainty. Now, the article itself says, it should be noted that since the neutrino flux has only an estimated 5% tau neutrino component, the possibility that new tau is a superposition of nu and nu mu cannot be eliminated using the results of the experiment. You must use reference 9, which is E531 corroboration I just showed you. Okay, so really goes back. Well, the great merit of Donut is to have observed the tau neutrinos interactions and to show you can do that. And that was to be used further with opera, for instance. But it's not the discovery of tau neutrino. The big question in the 70s and 80s, I recall, was whether there are more families of neutrinos. We beautifully showed the standard model work with 2 families, and all of a sudden, a third family was found, and miraculously, this worked very well. So there could be many more, as long as the total charge of each new family of quarks and leptons would be 0. This was a question of great importance for nucleosynthesis and cosmology. It's still a question of great importance for cosmology, and the cosmology measures a number called number of neutrinos, which I would love to understand what it means. The construction of LEP was decided by CERN Council in 1981, before the WNZs were observed at the proton-antiproton collider. That gives you the trust, the confidence people had with the standard model in 1980 to build a 2 billion infrastructure based on the standard model, not having seen that WNZs existed. Construction started in 1983, and the big scare at the time was the number of neutrinos. Now, LEP was on mission to find out. This was clearly one of the first scientific objectives. Now, physics at LEP was studied before LEP was approved, and one of the big contenders were our friend John Ellis. And he loved to invent words like zedology. Now, you can Google up zedology and see what you get. The discussion was that this could actually establish the number of constituents of matter, and he wrote down the Z2 FF bar partial width for getting the rho parameter. And he concluded that the total width would be 2 to 3 GeV, and then worried about the disappearance of Z boson. The above results are encouraging in the sense that Z peak is large and dramatic as long as there's not too many generations of fermions. So imagine the Z all of a sudden decays into 1,000 families of neutrinos. There would be no Z. It would just completely washed out. All you would do is decay into neutrinos. So, so imagine like the LHC finding no Higgs. Huh? All right. So the machine was built with 4 experiments. That was something we probably would struggle to do again. And they were underground like this. Sam Ting's experiment was close to Steinberger's experiment, which was kind of tickling. And you can see this is a bigger circle you can build between the mountain and the airport. Okay. Before LEP started, there was a beautiful article I already mentioned, because I really read this article several times, which explained what was the status and what were the reasons why this number was important. In particular, the helium hydrogen ratio. They said it could get an astrophysical limit from the size of the burst in the supernova in 1987. Data were published. You could also try to get it from the W's and Z's. The problem with hadron colliders is that you don't have The problem with hadron colliders is that you don't see all the decays, and you don't know the initial state cross-section. You can't really get the total width out of it. So it's difficult to, if there's 4 or 5 families of neutrino, all you see is a bit fewer z's, but then the problem is that you don't know what is the total cross-section for that. Anyway, there was a number of 2 plus 0.6, n equals 3, perfectly compatible with data, 4 families to provide a reasonable fit. So we were encouraged to go and find out about that. Now, the Z width would be made of 1.7 GeV for quarks, 84 MeV for each of the 3 leptons, and 170 MeV for each neutrino. The neutrinos are about twice as much as the leptons, because they have both right and they have both GeV and GA in their couplings. One more neutrino would increase the total width by 7%. So all you need to do is measure the width precisely enough, and you get done. Now, the first studies, and I have to say I committed that, elaborated a 10-point scan measuring the muon cross-section for a whole year to get a precision of about 20 MeV on the Z width, showing little understanding of the problem, I have to admit. Now, a closer look at the line shape in 1987. I started doing this a bit later. And see, the problem is that these electroweak programs, which were implementing the QED radiation, there was no way to put a force neutrino in it. They were standard models. So we had to talk to them and make sure we could get something consistent. And there it was totally obvious what you had to do. The whole difference is at the peak. Okay, that's all you need to do. Gary Feldman, him again, put this all down in equations in a Mark II physics workshop in February 1987. And the physics of it is that the peak cross-section is the coupling to the initial and final states divided by the total width squared. So you increase that 7% to 14%, and you are at the peak, and you can use the hadrons. It's even better for the hadrons. You have the hadron width and the total width. Since the hadrons have most of the total width, there's a cancellation of uncertainties in the ratio, and this becomes very powerful. So it showed that about 5,000 events, you could get a 3 sigma effect. Now, that's him. I guess that must have been Michael Peskin. Anyway, so we figured it all out. This is the formula proper. These quantities are all measured at the peak. So what you need to know is where the Z peak is, and then run. So we had, of course, our own internal proposals, which I'll skip. Labs started to run. We had the first events in August. Sometimes we really started in September, and we ran for 3 weeks. In 3 weeks, each of the experiments collected about 3,000 hadronic decays. They were beautifully visible. There's no way you miss hadronic decays. It's a bit easier to miss the E plus E minus, mu plus mu minus tau decays, because they're only 2 particles, and if they're aligned with your cracks, you'll miss them. But the hadron decays are very easy. So on the 13th of October, 89, L3, Opal, Delphi, and Aleph, and also Mark II showed, Mark II published on the 12th of October, showed the beautiful line shapes with only Aleph daring to put the neutrino curves on it. I guess we talked to the right theorist. And this was a source of many jokes among the CERN population. Everybody was giving the same talk. But that's a small detail. And this secretary was very proud of herself, said that her line shape was the prettiest of them all. Cecilia, you're doing jokes. I do jokes. Okay, and so all the papers are here. Interestingly, I was very proud of that. The LF number was better. That's because we knew it coming, and so we had probably prepared a little bit better the luminosity measurement. Anyway, when you put all these numbers together, the world average was 3.11 plus minus 0.16. And so in 3 weeks of data, we had only 3 neutrinos. That was really quick. And not as good as priority violation on 25th of December, of course, but we were quite happy with ourselves. Now, this is what we wrote. This was an interesting piece of work to write this with Jacques Scheinberger. Jacques Scheinberger wrote this sentence: this demonstration that there is a third neutrino confirms that the tau neutrino is distinct from E and U neutrinos. You can see where it's coming from. I wrote, the absence of a fourth light neutrino indicates that the quark-lepton families are close to the 3 which are already known. The 3 which are already known refers to the 3 neutrinos because we'd done our research at that time to understand what was the status of the tau neutrino, whether it was a discovery of the tau neutrino or not. It wasn't. We just confirmed it. Okay. When we did this, I want to show this. Cecilia commented that the number of neutrinos could be smaller than 3 if there were right-handed sterile neutrinos around. Of course, the Z would produce a left-handed neutrino, and the heavy part of the left-handed neutrino would disappear, so you'd have a smaller coupling. Now, we've understood this very well now. That was quite exotic at the time. I'm very pleased to have found this article again. At the end of LEP, everybody had changed their luminosity monitors, and we had a very precise measurement consistent with 3. It's about less than 3 by 2 sigma. I think it would be interesting to measure it again. Right. Oh, measuring it again, you have to go to the FCCEE. We are preparing this. We're going to have a CDR at the end of the year. We're going to do 10 to the 5 LEP luminosity with a 100 kilometer Z factory, which can go up to the top threshold. And with that, we can go directly measure this ratio. The gamma Z, put ourselves above the Z, measure the recoil gammas, compare the invisible to the electrons, and divide by the ratio of the standard monopartial width. This is very safe, and I think we can go an order of magnitude over LEP, or maybe even better. Right-handed neutrinos, that's how this should have been written, right? 0 minute, no, thank you. So right-handed neutrinos are singlet, they have no weak interaction, no electromagnetic interaction, no strong interaction. We can't produce them, we can't detect them. Why should we bother? Okay, so this is a professor which has a tie, that can't be me. Along with antimatter and dark matter, we recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. Of course, you know the story with the seesaw. You're actually mixing the heavy and the light neutrinos. There's a big mass splitting between the right-handed and left-handed neutrinos. And so the light ones have a small component of right, and the right ones have a small component of left. Anyway, the result is that they are heavy neutrinos. In that particular energy region between 10 GeV and 100 GeV, they have a lifetime, and you could see very, very beautiful events of that type. This is what FCC can cover. Couplings down to 10⁻11, which is exactly where the seesaw says you should go. Okay, so tau neutrino was discovered in the wake of the tau lepton discovery as a spin 1/2 neutral particle produced in tau decays. It took until 81, 86 to establish that it was indeed the isospin partner of the tau. In 89, it took only 3 weeks for LEP and SLC experiments to demonstrate that there are only 3 families of active neutrinos. Charge coupling of neutrinos were measured to premier accuracy at LEP from tau decays. These results stress the important contributions of colliders to neutrino physics. We are now planning a fantastic Z factory to enhance for sign of further neutrinos, the right-handed ones. Thank you.
Thank you, Alain, for this beautiful talk. So we have time for questions. Witold, give your name, please.
Witold Kozanecki, Saclay. Alain, I vaguely remember that at the lepton-photon conference at Stanford in '89, in the summer of '89, there must have been a limit from SLC on the number of neutrinos, or maybe Gary remembers.
That's right. That's right. There was a first measurement that was consistent with 3, but also with 4. And at the end of the, I think I've reported it in that slide. This was the SLC measurement. That was the one which appeared just before that date, the 13th of October. So 12th of October, this was the numbers from SLC.
Hi, this is Adam Bernstein, Lawrence Livermore National Lab. Earlier in your talk, you talked about this issue of direct versus indirect detection. I just want to comment that that sort of misnomer also exists in the dark matter field, where we work on direct dark matter detection, and that is kind of a somewhat arbitrary division between what's perceived as indirect astrophysical evidence versus so-called direct detection in a detector. But of course, there's numerous things that go on in direct dark matter detection that make it equally indirect. And so just a similar sort of problem prevails in other parts of physics.
I think it would be better to talk about model-dependent, model-independent. That's a much more quantitative statement. I think direct is very subjective.
Carl Albright from Fermilab.
Hello.
I just wanted to add to your history of the tau-neutrino. In the Bergen Neutrino Conference in '79, Robert Schrock, Jack Smith, and I proposed using D sub S to produce tau neutrinos, and then through a beam dump experiment, and then using the tau neutrino production of taus with a jet defining one vertex and the tau decay defining a second vertex as a way of really convincingly producing, identifying the production through tau neutrinos.
Quite.
You mentioned...
I mentioned donut because...
You mentioned those things, but I just wanted to...
Right. Sorry, the history of that is very old, I realize.
I probably missed it, but what is your final conclusion today of the existence or non-existence of sterile neutrinos?
All right, that's a good discussion. It's a good discussion. I think at this point in time, there's no convincing evidence for sterile neutrinos. There are mysteries in the short baseline, but there's no convincing evidence for sterile neutrinos.
So does everybody agree in the room on that?
Of course they do.
Any other question? Oh.
What was the contribution of the Gran Sasso thing to this, tau, the existence of tau neutrino? I mean, I didn't really follow the history, but they were making big business out of it, that neutrinos had actually produced tau on the Earth.
The Gran Sasso used the same technique as Donut, to detect tau neutrinos. It wasn't, they believed tau neutrino existed, otherwise they would not have invested so much in an experiment that was so far to do it. Let me just, to introduce the point that I'm sure Gary will make again, is that one of the things which E531 did is to normalize themselves to neutral currents. Because neutral current, if there are tau neutrinos, they will do neutral currents as well as everybody else. And that's very important for oscillation experiments. The neutral current, it's not in this slide. It must be in that paper. Yeah. They talk about neutral currents as a way to normalize and be sure that the total flux is correct, because it's the same thing that Snow did later, etc., for normalization. And so I'm sure this will appear when we discuss the appearance of tau-neutrino in oscillation. Ask Gary that question.
Tordek of Uppsala University.
I think this is completely out of my talk.
I see.
Okay, there is.
Gary Feldman, Harvard. I just wanted to add a little bit of unknown history to this, to part of this. I happened to be on the Fermilab Program Advisory Committee when the donut experiment came up. And I raised the issue. I said, we already know what the result of this experiment is going to be. Why do you want to do it? And I got shouted down by Pure Kane. So at that point, I figured I just better be quiet.
Alain, you want to comment on that?
No, I think this is not every experiment is built to make a discovery. So, you know, the fact that they demonstrated the technology and the beam was beautiful, I don't want to, I think it was used by Opera as well. I think that's a perfectly good set of honors. What I don't like is to see discovery of the tau-neutrino in 2000. That is not right.
Okay, so we have time for another question, maybe? No, I don't see any, so let's thank Alain again.